Welcome everybody to this Friday's webinar organized by the Euro Practitioners Forum. My name is Torkel and I'm the organizer, so you will mostly not be hearing from me. We will begin with a short introduction from Ruth Kaufman, who heads the forum. And then after that, we will move on to the presentation by Ryan, and you'll hear more about that later. I want to say that we will not be taking questions during the presentation, but at the lower right of your WebEx window, you can find 3 little dots, which are called panel options. And if you click them, there should be a possibility to open a Q&A tab. And in that tab, you can post a question as we go, and I will note them down. And I will also be kind enough to try to pick them out of the chat if they appear in the wrong place. But please try to use the Q&A window. And then we'll try to do a roundup of questions at the end, where you may be asked to unmute yourself if you want to talk. Otherwise, I'm more than happy to read out the questions and hope that you get responses, that I understand the question well enough. So the meeting is being recorded. As I said, we will make the recording available after the fact, but it will take a couple of days, I think, before this is posted anywhere. That is, I think, all I need to say for the introduction. So over to you, Ruth.
Thanks very much, Torkel, and welcome everybody. It's great to have so many people here. We actually had a record number signing up for this particular event, and we don't expect everyone who signed up to come along, but it's great to see so many of you already in the room. Just to say, it would be really nice because it's from all over. It'll be from all over Europe and wider, certainly from the States as well, and maybe even from east of Europe if you can stay up late, if you stayed up late. So do introduce yourself in the chat, say where you're from, and we'll have a couple of questions for you later on. So if you can get slido.com opened and enter the code, you'll get another chance to enter that code later on. But I just wanted to do a few introductions. As Torkel said, thanks Torkel, I'm the chair of the Euro Practitioners Forum. And the purpose of the forum is to be a natural home for people who work in operational research but outside academia. It also welcomes people who work inside academia, but it's really about the practice of OR enabling us to network, to share ideas and to enjoy ourselves while we share those ideas. So occasionally physical meetings as well as online meetings. I'll just say a little bit about what we've got coming up. The next First Friday webinar that's booked in is based on taking July and August off and coming back on the 6th of September, where we have Alex Chan from Aldi, who was an Edelman finalist. And the Edelman, even though we come from Europe, where we have the Euro Excellence in Practice Award, I have to say the Edelman represents the finest award for practical applications, and even to get to the finals is a great achievement. So we have Alex Chan from Aldi talking about their work. If there is anybody on this call who would like to give a webinar themselves and would like to take on the Friday slot, which would be the first Friday in July, do put something in the chat or write to us separately, because we can put something on at short notice. It's just that we would expect a rather thinner audience in July, but still a well-informed and interested audience. So don't be put off. Let us know. But in general, first Friday of the month should be in diaries. Our next event that is coming up in July is at the Euro Conference, the biggest event in Euro for operational researchers. We are running the practitioners stream throughout that conference. So every session, there is something which is aimed specifically at helping people who work in practical OR to improve their skills, to meet each other, to learn from each other. There's a hell of a lot else going on at the conference as well. So it's if you haven't booked, as long as you don't particularly want to speak yourself at the conference, but want to participate, all of our sessions are participative. It'd be great to have you there. And if you are going to the conference, or if you know somebody who's going to the conference, do flag this up to them. We've got a page, the final details of all speakers aren't up, but we have a page which has the descriptions of every session and the panel sessions and the audience involvement sessions. on its own page on the Euro website, the Making an Impact webpage. So do have a look and do join us at the conference if you possibly can. We have a second face-to-face event coming up in October, and that is at the University of Coimbra, which is one of the oldest universities in Europe, certainly the oldest in Portugal, beautiful town in Portugal. And we would really encourage anybody who would like to put forward a paper to that conference to put it forward. We've extended the deadline to July so that anybody who's going to Euro can get Euro out of the way first. The theme is OR in collaboration, because basically you can't do OR without collaboration. You can't do OR in practice without collaboration, and collaboration is a really significant theme that we wanted to bring out for this conference. And of course, that's very much associated with the talk that we have coming up later on at this event. So again, if you've got any thoughts or comments on that, let us know. But it'd be great to meet you in Coimbra. The Coimbra conference is free. So all you have to worry about is the travel and the accommodation, one-night accommodation, and everything that's going wrong while you're out of the office. But that's another matter altogether. So those are the big things that we have coming up, and we would love to see some of you there and actually meet you in person. A couple of questions now about you, so that to help Ryan giving his talk and positioning himself. So if you're there on slido.com, if you go to polls, so we're not looking at the Q&A, but go to the polls and just let us know, do you use OR techniques on their own, machine learning on its own, OR and machine learning, or neither? And gradually we see the results coming in. Only 6 of you have made it so far. We currently have about 40 people in the room, so do keep going. So what we get the feel of from that, I think, is that generally about half of you are already combining machine learning with OR, and about half of you aren't. And of the half who aren't, most of you are operational research people, but there's somebody out there, or several people out there, who are lone machine learners. So thank you. I'm going to go on to the next question. Are you stochastic, deterministic, or not an optimizer at all? Basically, I think whatever the detail turns out to be, it's predominantly a deterministic room for you here today, Ryan. And stochastic is, well, I suppose it's still a quarter, isn't it, if you add the both and the stochastic? So yeah, let's
it's really interesting.
Just, I think that's probably stabilized. Excellent. Well, it's always nice to know a bit about the audience. So thank you very much for doing that. And if you want to add any comments in the chat and say any more, make your refine your answer or make any comments, then please do. But now it's my pleasure to welcome our speaker, Ryan O'Neill. So Ryan O'Neill, sorry. So Ryan has a huge range of experience in different aspects of operational research. Now his CV says he's worked as an OR analyst at MITRE. I had to Google MITRE, and it said it's the most important company that you've never heard of. I'm not in a position to comment as to whether that's right or not, but certainly half of it is definitely right. He's led software teams at organizations which include the Washington Post and others which I think Europeans will be less likely to have heard of. He certainly led decision engineering departments at US food delivery companies Grubhub and Zuma, involved in forecasting, scheduling, routing and simulation. And he's got PhD in OR from George Mason University. And he, having done all of that, he was a co-founder of NextMove. We're allowed to pronounce it NextMove. We're just not allowed to spell it NextMove. Is that right, Ryan?
Yeah, we say NextMove, but it's it is NextMV. Yeah, it's named after the Unix command.
Oh, okay. You see, I'm not a Unix person, obviously. And Ryan is not just the co-founder, he's also CTO. So without any further ado, delighted to have you here, Ryan. Very excited to hear what's going to come up. And I shall stop sharing and pass over to you. Thank you.
Thank you, Ruth. And I will start sharing. I think we managed the transition all right.
Hey.
Excellent. Okay. So yes, thank you, Ruth, for the intro, and Torkel for hosting us, and thank you to the Euro Practitioners Forum for having me. It's really a delight to be speaking to you all today, and thank you to everyone who's attending. I'm obviously very passionate about this topic, so I'm excited to share some of the things that we're working on here. I think I need to pull this over here so it's not doing an infinity mirror. All right. So today's topic is what we're calling the 3-model problem. And this is a method that we're starting to use to combine machine learning and operations research through horizontal compute. I should say up front, this is not something that we created conceptually. It's something from the literature that we're applying, but today's focus will really be on sort of the operational mechanics of how you apply this in technology stacks. So I'll skip most of the intro. I'm Ryan. This is my cat. She actually, may she rest in peace. But yes, I'm the co-founder and CTO of NextMove, where we build decision ops platforms and work with a lot of optimization models and a lot of optimization solvers and things like that. And a lot of my experiences in on-demand vehicle routing and machine learning models. So again, today's talk is on this sort of what we call the 3-model problem. And if you are in the operations or in the on-demand space in any way, really these are kind of like the 3 mother sauces in French cooking. You need to be able to forecast demand. You need to be able to schedule some kind of supply to meet that demand, and then you need to be able to actually do real-time operations around providing some kind of service, whether that is delivering goods or anything else. And so these are represented here by these three paintings. So we have forecasting, demand, scheduling, and real-time routing. So this is not actually about a popular Netflix show, but it does have some sort of science fiction aspects in that when we talk about these problems a lot, primarily we see and have traditionally applied these problems in a deterministic sense, right? And obviously that's not how the world is. Like we are forecasting for a reason. We're forecasting because we don't really know what's going to happen. We would like an estimate of what's going to happen in demand for our businesses in the future. And that forecast has, of course, built-in error. We're basing schedules off of this erroneous forecast. We know it's going to be wrong, and yet we're using these frequently using these deterministic models anyway, because that's sort of what we reach for and what we know how to work with. And then at real time, we're also frequently applying deterministic models. So we'll touch a little bit on the models, but the topic really is about, how can we take sort of some of the same technologies that we've already built and sort of stochastify them in simple ways using horizontal compute as it has sort of been applied to other things like data access and data querying and things like that. All right. So it's always useful to go back in time a little bit. So let's start by going back to the advent of operations research. In the beginning, there sort of emerged 2 branches within OR. And certainly in my education at George Mason, we had stochastic optimization, or stochastic operations research, I should say, and deterministic operations research, right? And they were very much separate paths at the time. It was, you studied queuing theory and stochastic processes in one, and in the other, in simulation, and in the other you would study linear programming, integer programming, and nonlinear programming, and things like that. And it wasn't until sort of later that you'd start to combine these a little bit, but it wasn't like you were taking stochastic processes and linear programming and mashing them together, right? You were building stochastic optimization on top of linear programming and integer programming, or you were doing simulation-based optimization. I think a lot of the way that we apply optimization and math programming in particular is in a way an accident of history. At the time that it was developed, linear programming in particular, we were really good at linear algebra, right? And so that became the natural vehicle for which we would model and solve problems. And so the matrix ended up being the engine right? And linear programming and integer programming were sort of built on top of that. If we look to the hybrid optimization community, they've had sort of the realization that there are general search strategies and optimization strategies that apply across many different optimization and optimization-like fields and are sort of unifying principles. And so many of the same technologies have sort of been developed outside of that context of, say, linear algebra, linear programming, integer programming, and are relevant sort of across these ways, right? So, you know, the precise nature of the vehicle or the engine that we use to solve these problems is a bit separated from like the why, right? And so in this world, deterministic modeling really became the common practice, and we all sort of learned math programming and things like that going through school, and then we graduate and we apply it that way. And one of the things that's nice about that is that math programming is sort of very structured, right? We learn the language to create models in, and then we have this common way of communicating and working with business stakeholders and so on and so forth. In a different track, machine learning with randomness, probabilities, and so on and so forth really has matured a lot. But blending the two of these things is hard. And it's particularly hard with this three model problem because, one, in topics like on-demand routing, we frequently have very hard constraints on how long a model can run for. So if I'm doing an online pickup and delivery problem, I might only have 30 seconds or a minute with which to optimize. If I'm doing a scheduling model, I may not actually have that hard a constraint on the operational runtime, but I likely have a person in the loop who isn't going to sit at their computer for more than a couple of minutes. And so I may be constrained in my runtime in other ways. And so blending these two things presents both mathematical and sort of operational challenges on the technology side. So let's look at the two of these from the optimization perspective and like what the current methods are and what they give us and what they don't. So, you know, again, a lot of us, as we saw in the survey that Ruth gave us, are applying deterministic optimization. What I found interesting about this is about half of the respondents were also using ML, right? And so it's an interesting question as to, well, you know, why are we using deterministic optimization frequently when we are also using ML? So we have this sort of inherent understanding of uncertainty in the world around us, and yet we're applying deterministic models. And there are good reasons for that. So deterministic models are repeatable. They're extremely repeatable, right? I run it and generally I should get the same output from the model, and that's a good thing because I can test it. They tend to have more defined performance, and this is not necessarily entirely generalizable, but I can understand the performance of a deterministic model sometimes more easily than I can a stochastic model, and therefore the solve time. And it's more straightforward. We have a math programming languages, constraint programming, things like that. The language about how we develop a deterministic model is well understood and has been developed for decades now. And yet they are obviously poor at handling uncertainty because there's nothing in that language, no primitives in that language for defining these models that actually handles the uncertainty. On the stochastic side, we get variable output for a given input. The performance characteristics are less defined. It really has to do a lot with how we model, and there's a lot of options there. So if you open up, you know, the Burge and Laveau textbook on stochastic optimization, you will learn about the L-shaped method. And what exactly are the performance characteristics of that? It's a little hard to say. It's a decomposition, right? And so you end up with these sort of multi-model scenario approaches where it's models communicating with each other and nested inside each other, and it becomes a lot harder to say this thing is going to solve and provide a good solution within 30 seconds. So there's fewer guarantees about things like solve time or even time to feasibility. They frequently require more sophisticated modeling approaches. In the stochastic optimization literature, you know, you have to think about things like recourse and non-anticipativity in models. So the models are just harder to build, but they are also better, obviously, at handling uncertainty to the degree that we can represent that uncertainty in the model. The The thing that I like, though, and I think the thing that does give us a little bit of an edge, is this sort of fundamental realization that under every stochastic algorithm, we are applying some kind of deterministic method of searching that space. And so you can see this in the simulation world. When we do stochastic simulation, discrete event simulation, we are running a deterministic algorithm on random inputs, right? We are generating pseudo-random numbers, which are deterministic and approximate randomness, right? And so we see it there. In things like stochastic optimization with the L-shaped method, we are building a deterministic model, and then we are adding randomness to it and modeling the interactions between master and subproblems. But the model itself is a deterministic model, right? And so this realization allows us to think about, if our models are sort of fundamentally deterministic, or I should say our algorithms are fundamentally deterministic frequently, the question really is, where do we put the randomness? Where do we put the uncertainty? And there are some options there. And so today we're going to go over one of those options. So today we have, again, largely deterministic models. Most of us are building deterministic models and putting those into production environments with the understanding and the knowledge that we are working in an uncertain world. And I think a lot of that has to do with the complexity of that reformulation and the performance characteristics of doing so. But it's worth investigating other options. And so today we're going to look at what we're thinking of just as the horizontal compute application of this, right? And so if you think back to earlier days of databases, it used to be that you'd run a database on your machine, right? And if you wanted to give lots and lots of people access to it, you'd have to let them connect. And eventually, they'd be running queries which would block tables and interact with each other and so on and so forth, and your database would no longer scale, right? You couldn't handle all the requests that were coming into it. And so technologies were introduced around things like sharding or partitioning or event-based mechanisms for managing data, where it would allow us to sort of scale data access and analysis horizontally, right? And it's kind of the same in the machine learning world. There are techniques where they have been able to take like extreme gradient boosting and things like that and parallelize them and leverage horizontal compute. And of course, this comes with sort of strings attached. There are some things it works well with and some it doesn't. But they have been able to apply this. And so I think we can apply this in interesting ways here too. And we've been also talking about this as sort of the no-need approach to stochastic optimization, where you still use the deterministic model, but what you're just giving it is essentially scenario data, right? And so is there a way for us to leverage what we have to take sort of a baby step past that deterministic modeling and just leverage horizontal compute and not have to think too hard about it? So let's dive in and explore what this looks like. We'll start with those three models, and then we'll start looking at where the uncertainty is and what we're doing with it in today and what we could be doing with it. So these are the three models that we're looking at. The first one is demand forecasting, the second one is shift scheduling, and the third one is vehicle routing. In demand forecasting, basically what we're trying to say is, how much demand am I going to expect at a particular time and place? These could be, pickup and delivery orders from restaurants, or they could be much more than that. It could be in-home healthcare. Really, so like how much of some unit of demand do I need to be able to service? And in these kinds of applications, really what we're trying to do is balance supply and demand in a way that both provides good service to the end user, right? So pizzas aren't cold. In-home healthcare workers don't miss appointments. You tend to have the same person, those kinds of aspects, with the needs of the supply. So people who are providing the services and work are getting paid well. We have predictability and those kinds of aspects within this. So it's a marketplace where there's predicted demand, there's supply which we may have control over or not, and then there's frequently sort of on the ground operational, sometimes real-time characteristics. And so that's how these things interact. In the first model, we're trying to say how much demand do we expect to have. In the second one, we're trying to say how much supply, given that demand, should I schedule or prepare. And then in the third one, we're trying to say, how do I leverage that supply to meet the realization of that demand in real time? This is how the data flows from each one of these problems to the next one. So if we focus sort of on the delivery version of this problem, frequently the way this will work in a production environment is I'll have historical order volume. From that, I will forecast order volume, frequently weeks, days to weeks in advance. Obviously, I'll have uncertainty on that. From that forecasted order volume, let's say we're doing delivery, I will have, for a given region that I'm operating in and time of day, targets for how many workers per hour, or sorry, orders per hour a worker can do. So for example, I may say at a particular time of day, I can do 2 orders per worker hour. At a different time of day, maybe I can do 5 orders per worker hour. And so things like traffic, congestion, the topology of a region, traffic speeds, the kind of vehicle that my workers are using, those all sort of matter. And those things help inform the unit economics of my operations, right? So at some delivery companies, for example, if they're operating at, say, 2 deliveries per driver hour, they'll be losing money. If they're operating at 3, they'll be making money, and somewhere in between is their break-even point. And frequently in these sort of high-volume industries, high-volume, low-margin industries, they're sort of riding that breaking point. They're straddling it one way or the other pretty closely. And so the ability to do this matters quite a bit. Okay, so they'll have forecasted order volume, which frequently is quite erroneous. These are stochastic processes that are with non-stationary distributions. Orders are coming in, demand is coming in, and especially if it's on demand, you don't really know. You don't have a necessarily great sense of how much it's going to be or what the error is. The general shape of it. From that, you're trying to say, how many workers do I need? This can actually be quite complex because if you're working in a gig economy model, you can go anywhere from all of my workers are on-demand gig economy workers to all of them are scheduled or somewhere in between. And frequently what we see is organizations will go somewhere in between where they provide incentives to workers to pre-schedule a shift. So that way they can guarantee some level of supply and service to their end users. And then they'll rely on on-demand workers for overflow. And so it can be quite complex. You'll also take into account worker availability, and frequently this is just asking, are you available at this time? Do you want to take this shift? If you do, here is frequently some incentive that would encourage you to sign up for it, which could be like a minimum pay or something like that. And from that, then you say, okay, these are the people that we're going to schedule, and this is how we're going to allocate that projected demand to overflow or on-demand workers or something like that. And these two models really are sort of at the tactical level. They're frequently days to weeks in advance, and they will frequently be updated as more information comes in. So in the real world, I will often forecast maybe 2 months out. I'll forecast again the next week. I'll forecast again the week after that. And each time I do this, I may lock in some decisions. Like I may say, okay, I'm going to release some shifts for people to sign up for them. People can take them, but I only want to release a certain number of them because I don't want to release too many. I don't want to have too much economic liability. And so these things will frequently be done sort of in a rolling pattern where you're sort of rescheduling and allocating or putting shifts into the real world and letting drivers sign up for them and things like that. This vehicle routing side is oftentimes the day before or maybe even the minute of or the hour of, depending on the use case. And so this is sort of the operational realization of everything that comes before it. Of course, people who are ordering food or rides or something like that, they're not subject to any of the decisions that are made on the demand forecasting or the shift scheduling side. They're just ordering food or ordering catch or something like that. And so this is when that demand becomes actual, right? And where do you need to send people, so on and so forth. And so your hope here really is that after all of these sort of tactical exercises that you've done up front, forecasting demand and releasing shifts and so on and so forth, you have enough people on the ground, but not too many, right? And so then this is the real-time realization of this is what are the routes and what are the assignments right now. All right. So we'll focus mostly on forecasting and scheduling. We may look, if we have time, at some routing. But forecasting and scheduling are interesting because they are directly linked, i.e. they take place at the same time, right? So I'll generate a forecast and then I will frequently run a scheduling model immediately after, and I may take action based on the output of that scheduling model. And so it's a good opportunity for us to sort of see how we can inject uncertainty from that forecast into the scheduling model. All right. So let's look first at what a fully stochastic version of this might look like just from a data flow perspective. So in this case, let's say it's a stochastic model. Let's assume we're using like the L-shaped method or something like that to fully outer linearize our search space. We take an historical order volume, we forecast it, we have targets, and then we account for uncertainty, and then we put that directly into our scheduling model. So our scheduling model has the uncertainty monkey in it, and it considers all of the different demand scenarios when it is solving, that is represented in the search space. And then it comes out with driver shift assignments that will account for that uncertainty in some way. And that might be sort of a robustness measure, i.e. The schedule adapts well to unexpected changes, or it might be just a minimization of cost or a maximization of profit under stochastic or under uncertainty, or something like that. And so this is the fully stochastic model flow. The important thing here is that the uncertainty goes from the forecast and from the data directly into the shift scheduling model, and that's where it's accounted for. So this is kind of an ideal scenario, but of course, anyone who's tried to do this knows that reformulating these models can be quite challenging. This is we're going from this world where everything is sort of deterministic and we just don't worry about it, to this one in which how do I take that uncertainty and put it into this formulation? And that can be quite challenging. So frequently what happens is we just say, I'll do the deterministic one instead. It's good enough. And we'll just operate according to that. Of course, when we do that, what's actually happening with the uncertainty is we're basically crumpling it up and tossing it in the trash can. And so it's not accounted for at all. There is no uncertainty monkey in our model. And our stochastometer just goes way down, right? And this is operationally viable from a technology standpoint, i.e. I don't have to change anything, right? If I build this model, I put it into production, if I don't have to do anything, I just run it. It's my deterministic model that I developed. As new data comes in, it just behaves sort of the same way, right? And so from that perspective, this is quite attractive, but obviously from the perspective of like profits and loss or business revenue or things like that, this may not be. So really the question is there a middle way? Can we get part of the way there with some of the benefits, right? And so, here's another one where we do a deterministic model. Again, go back to the recognition that under many stochastic technologies, there is still a deterministic model, right? And so if that's true, we should be able to take the deterministic model that we've already built it, and we should be able to get some benefit from applying stochastic inputs to it. Well, we have the uncertainty. We have that from our forecast, right? So can we just now use that with our scheduling model? And so in this scenario, what we're doing is we, again, forecast based on historical order volume, and we just produce multiple forecasts, right? And then we send those over to the shift scheduling. These are all the same deterministic model. And so we can leverage, here we can leverage horizontal compute. And we can, say how many workers do we require at each time. We can take worker availability, and we can do shift assignments, and we can just sort of select among them. So this is a path for leveraging uncertainty. But, where it sort of breaks down is down here, what do I do with these? I've got multiple schedules. I've got multiple forecasts and multiple schedules. Do I just pick one? Do I just pull it out of a hat and say, this is the one I'm using? That's obviously not going to work very well, because the real world is going to be random, but there's no particular reason to believe that it would be the one that I pick. And so this is where consensus comes in. And so this is based on a paper by Bent and Van Hentenryck, where they call the multi-scenario approach. And what we're going to show just operationally is how can we take on the left what's called an ensemble function, and on the right what's called a consensus function. Functionally, they're the same thing. Ensemble methods are just applied to machine learning models like forecasting, and consensus functions are applied to operational models like optimization. And so in this case, what we're doing is we are generating historical orders. We're taking in historical order volume. We're generating different forecasts. We are then ensembling those together to produce the forecast. The reason that we do that is it allows us to take outputs of different machine learning models and combine them to make them more effective. And then we will leverage horizontal compute, do a scheduling model for each of these, and run a consensus function on those, which says, here is the schedules that we should go to. And it takes into account some degree of stochastic information. All right, so technology-wise, this is what we'll use. And for the demand forecasting, so again, we're ensembling a few different models together. So I'm going to use stats models. It has a Ceramax forecasting module that we can leverage. Meta's Profit, which uses I forget what they called it, but it's maximum likelihood estimation and linear to find linear terms. And then a least absolute deviation regression model that we have that's built with OR tools in the modeling layer, Skip for the solver, and again, it's a lab regression, and that's based on another interesting paper called Local Warming by Robert van der Bij. We can take the output of all of these and ensemble them to produce a forecast. And so the idea with that is that each one of these models will understand variance in different ways. And if we combine them, we can get sort of the combined learnings of those different models and generalize better. We can also use them to generate input scenarios to our shift scheduling. And so for our shift scheduling, we'll just use an integer programming solver that we've built for that using highs, and at the end, a custom consensus function. These two are pretty simple. The ensemble is just averaging. You could do it differently, but that's what I'm going to do. And then the consensus function is a little bit more complex, but it's not very hard. All right, so we've talked through the workflow and how sort of uncertainty plays out with these models a little bit. Demand forecasting, shift scheduling, vehicle routing. But the problem that we ultimately want to solve is really this: how do I go from historical data, understand the randomness and the variance associated with that, into a schedule that will adapt well? Just for references before we look at it, we talked about a little bit about in the Databricks world, we had sharding and events. In ML world, there's XGBoost, and more recently, there's leveraging lots and lots of GPUs. So in large language models, those get split up across thousands and thousands or tens of thousands of GPU worlds. We mentioned the paper by Bent and Van Hentenryck. That's where they introduced the multiple scenario approach and consensus functions applied to it. That's quite literally what we're doing here with the the shift scheduling one. And there's also been interesting work in the solver world recently on highly parallelizable solvers. LinkedIn recently built a linear programming solver called Dualip, which is supposed to scale to, I have not tried this, but it's supposed to scale to, I think, trillions of variables. Because I assume what they're doing is they're representing the LinkedIn network as a network and using a linear program to solver. So there are interesting applications within solver development already on how to leverage horizontal computing in different capacities. So if it's really this simple, why don't we see it frequently? And I think there's a few reasons. One is that there are models for this which this will not work well. And I think if you look at like what Warren Powell has been writing a lot about with these what he calls sequential decision models, some kinds of models will become more and more challenging to model this way. If you have lots and lots and lots of stages, right, it's going to be harder and harder to generate scenarios in a meaningful way and put them into this kind of infrastructure. That's not really the case for us because we're looking at these sort of single stage models. We're looking at forecasting order volume, shift assignment, vehicle routing. We're not then going 5 stages down the line and saying like, well, what happens when it's raining outside on Tuesday. And so if there's these sort of clean interactions between the models and they're well defined and well contained, they have a good surface area, this kind of technique can be more applicable. Another is hosting. This requires a lot of infrastructure, right? And so if I'm going to leverage horizontal compute, I've got to build out a lot of stuff, right? And so a lot of those tools are now available, which makes some of this easier in that you can build a model and then massively scale it up and run lots and lots of instances of it. Before, that was something that you'd have to build out yourself. And so that was a barrier to entry for some of these kinds of things. Another one that makes this hard is the consensus function. And there are models where building consensus among a disparate source of decisions is hard. And then there are models where it's easy. And so, this is kind of one of the reasons why OR people will never be out of a job is even if you simplify stochastic optimization down to something like run a bunch of models in parallel, you still have to design something that's complex at the end, which is, well, how do I take the output of all of these things and mash them together, right? Make a strawberry smoothie out of it that is actually operational and feasible in the real world. And has characteristics of them. And there are some models for which that can be quite simple, and others where it can be rather complex. All right, so it's time for the speed run, and so we'll very quickly go through these models in production. I'll probably not share the terminal. I'll just show these through our web console. But what we're going to start off with first is a forecasting model, and so what I have here is an ensemble forecasting model. Where I have inputs, whoops, not that one, this one. Inputs that are just historical order volume. And they look like, pull over my terminal or my editor because, here we go. It won't, the file's too large for it to display. They're pretty simple. They basically have a date and a time of day and a count that represents how much demand do I expect? And these could be things like orders. They could be, car service requests. They could be in-home healthcare. It really packages. It really could be anything. Just some sort of unitless measure of how much demand that I can match to supply in some way. And that's really it. And so the forecasting model operates based off of this. And what we have, I'll look at one of the outputs, is different forecasts depending on those different technologies. So we have an OR tools forecast, which gives us different forecasts and counts. And we have a profit forecast and a stats models forecast. And then we ensemble them together and we have another forecast, right? And so when I run that, I get something that looks like this in my output. And thank you, Torkel. I think we're approaching the 5-minute mark. And so now what I want to be able to do is ensemble that. And so you can see here we have this model where we've ensembled these forecasts into sort of this mishmash of all of them. And so then the question is, how do I then generate data that I can use to do scenario planning for my shift scheduling? And so we'll just look briefly at what that is. And so I'll scroll down here, and you can see this is just a simple visualization we put together using Streamlit. These are the actuals versus forecasts for the different models. And you can see there are parts, they're just coded by color. There are areas where like stats models is way off, and there are areas where it's actually really close. The blue is the ensemble model. And then if I minimize this, I get histograms of errors. This is actually designed data, but what I would expect in the real world is that frequently the ensemble model quite outperforms the others. And so that's what that looks like. And so this is the ensembling part of it. And next what we can do is look at the batch, the scenario shift scheduling part of this. And so here we have a shift scheduling model, which is based on highs. I have the formulation for it in the slides if anybody's interested, but we can go to that later, or we can follow up afterward. And what we'll do is take those forecasts from the ensembles, and we're going to generate input sets. And so here, I need to change this to 2023. Here we have worker availability, and this is just something that workers have given us. So we ask them, when can you work? And then I'm going to use the ensemble forecasting model, and I'm going to use the ensemble outputs. And so what it'll now do is generate input sets that I can use. And what I'll do now is I'll run all of these through my shift scheduling model, right? And so after I do that, I can create a batch experiment where I say, here's the name, use that particular input set that it just created, and run it through all of them through the model. And the output of that will look something like this. Group this by, there we go. So here are 7 runs. In reality, this would probably be hundreds. And the objective value on these different runs has this range to it. And you can look at lots of different custom metrics like the duration or how many constraints or other things that are coming out of the shift scheduling model that way. When I look at any one of these, let's look at actually 3 of them. What I'll get are shift schedules that look like this. And so in this first one, Yawning Lemur, these are whimsical names of workers, is working from 2 to 10. And we have scheduled flabbergasted blobfish. They're also kind of hard to say. In the second one, Yawning Lemur is also working from 2 to 10, but we didn't schedule flabbergasted blobfish. And in the third one, Yawning Lemur is also working from 2 to 10, and I didn't schedule flabbergasted blobfish. And you can go on, right? And so I'm getting out of this multiple schedules. Some of them have things in common, right? So if I schedule Yawning Lemur in all of them, it's a good idea to schedule Yawning Lemur, right? But if I didn't schedule flabbergasted blobfish in most of them, maybe I don't really need that person. And so finally, and this is the last piece, I need some way of developing consensus among all of these different models. And so then what we have is just a consensus function. And so in our case, this is very simple. If I schedule a particular worker 50% of the time in 50% of the outputs, then roll the dice and schedule them with a 50% probability. If it's 100% of the time, you're definitely scheduling that worker. And then you average the start and end times together if you schedule them, right? And so then what you end up with is a shift schedule that looks pretty representative, where it's sort of the whole set. And so, when I run something like that, what I end up with is, again, a schedule, just like the other schedules, but these the the workers that are scheduled are sort of an amalgam of all of those. And the idea is that this adapts well to the variability that I'm going to see in the real world. Now, of course, this is much harder for something like routing. The scheduling model here in this particular case is easy because these people are independent. I either schedule them or I don't. If I schedule them, they told me when they're available. If the models have scheduled them, then scheduling one or the other, they don't impact each other. There's no constraints on that, right? And so the question is just how do I sort of adapt all of these scenarios together into one that's can meet different types of uncertainty. All right, so that was the speed run. Quick takeaways, stochastic optimization, deterministic, they're all great. What we're trying to do with horizontal compute is leverage some elements of stochastic optimization in a deterministic setting. That's really unlocked by infrastructure, and then some reasoning about things like consensus and ensembling. And so this is one path among many to sort of start to combine these technologies in interesting ways, but there are other ones. There are fully stochastic solvers that you can look at. There's also things like Gurobi had a blog post on avocado price optimization where they inject regression coefficients directly into mathematical models. And so you can also do things like that. And that's the end of my talk. So if you want to look me up, you can find me on LinkedIn. I'm also Ryan J. O'Neill at GitHub. And you can find more information about NextMove itself at nextmove.io. That's nextmv.io. And thank you for your time.
Thank you, Ryan. This is a very interesting talk. We have 7 minutes for questions. So feel free, people, to add the questions in the Q&A. I can start with the first one, and it seems possibly like something that takes a little while to explain. There's a question from Mark Stone, where he asks you to spell out more clearly the math of the consensus function, including for dependent situations.
Yeah.
This seems to be the meat of the whole thing, and I agree with that.
Yeah, and I think this is where it starts to it can get tricky. So with the scheduling one, it's easy because I can just say, if a person is always scheduled in every output, then we have consensus, right? Or most of the time, then I probably need to schedule them. And I can take their start and end times and I can sort of smoosh them together from all the different outputs. In something like routing, it's a lot harder. So I believe what the Bent and Van Hentenryck paper did, if I remember correctly, was they looked at all of the outputs of the models and they chose the one that was most like the others. Right. And so so that can work well. The problem there, and again, this is why we'll never be out of a job, is how do you define that norm? What is the distance between two model outputs? And that is non-trivial.
Right. Yeah, but can I ask a question while I'm waiting for someone to write something?
Yes.
In this independent scheduling consensus that you are doing, do you post-process this consensus in some way before you do the routing? Because, I mean, in principle, you could wind up in nothing.
So in this particular case, let me find. There it is. So in this particular case, typically what's happening is you set, and these are typically set by operational people based on P&L and sort of region capabilities. What you'll have is you're trying to sort of match these two things together in a way that is reasonable, right? And so you have a projected supply and demand curve, and the supply in an on-demand problem could be zero. It can frequently be zero because you can pull people from the field. So if you're, for example, driving for one of the big delivery companies, most of the time, anybody who has that is logged into their app is considered supply. right? But they are not necessarily, there are no service guarantees, right? And so you can send offers out to people. This is getting a little into the weeds with operations on these platforms, but you can send offers out to people and they can ignore them or reject them. And if they're not a scheduled worker, that may have absolutely no impact to their future work with the app. And so the reason that you're actually scheduling people is you're saying, I will give you, some reason to be available and to do what I'm asking you to do. And so as you do that, what you're doing is essentially taking on economic liability. But yeah, I mean, you could end up with a schedule where there's nobody scheduled, and that might be the most sensible thing to do at a particular time of day or in a particular area. Or you could end up in a world where you're just massively overscheduling because you're trying to get really good service levels.
Thank you. Do we have more questions?
Can I ask a question while we're waiting? Because I'm sure there are. That was really, really interesting, Ryan. So thank you so much for that. Just coming back to this question of practice, how do you judge whether your schedules are better or not when you're using this approach? And can you give an estimate of how much better, if there is a way of judging?
Yeah, it's hard. A lot of the time, what we've done in the past is sort of look. Ultimately, what you're trying to do is get at some ratio of supply and demand, right? And so, what we've done in the past a lot is look at historically what have service levels been in a particular region at different times of day with different ratios of that supply and demand. And so frequently in the real world, what they'll do is they'll do that analysis and they'll say, like, in order to operate in College Park, Maryland at dinner time on a Friday, I need to have between, I can handle up to 2.5 orders per driver, and I don't want to get beyond 3, right? And so then they'll usually have these sort of ranges and ballpark estimates that they're trying to hit. Those will also be based on sort of economic indicators from the P&L side of things, which will say, like, I can't spend any more than this on my driver supply or on the incentive management to do that. So frequently it's a range that's developed out of historical data. The problem with that, obviously, is that as the real-time routing algorithm changes, it's not going to, the historical data doesn't account for those changes, right? So if you change the algorithm to do more bundling, for example, you should have more efficiency in the algorithm in real time, which will not be accounted for in the historical order volume. And that's where things like simulation come in. But those are, again, that can be hard because when you're simulating these kinds of environments, it can be a little challenging. There are so many things that are random that sometimes it's very hard to calibrate that simulation to the observed historical data. But yeah, frequently it's a historical order volume with service level, which will determine service levels. If I staff at this level, I will see, and I get this kind of order volume, I'll see these kinds of service levels, and then essentially a profit loss indicator from the business side.
And if it comes down to profit and loss, how much difference has this made? So I don't know if you've got any examples of where you've actually applied this approach and you can see savings, and what sort of order of magnitude are we talking about?
Yeah, I can talk about Zoomer a little bit because we focused a lot on efficiency when we were there. We would typically, we were doing restaurant aggregation. Essentially, we didn't do a marketplace like Grubhub or those guys, but basically restaurants would sign up to use us just for delivery, and they would send us the deliveries and we would pick them up and take them. So we were essentially consolidated delivery services, trying to sort of provide like a Domino's or a Pizza Hut kind of, or Papa John's kind of thing for restaurants. And for us, typically it was like if we were operating at below around 2 orders per driver hour, we were losing money. At 3, we were making great money, and at 2.5, we were breaking even. And it was a little bit dependent on the region, and there were regions that we could operate at 3, and there were regions that we could only operate at 2. And 10 cents in either direction was the difference between territory net positive or not. And so, mostly you don't see the forecasts better than like 10 to 15% off in these environments. And so scheduling can be quite challenging. And one of the things we see with a lot of players in this space is that they are moving toward a hybrid worker supply, where they are using incentives to guarantee work, because that's really the only great way to guarantee service. And if you want to get something to an end customer within 15 minutes, 20 minutes, an hour, you need some mechanism for saying, yes, we will honor our promise of getting this to you. And that's very hard to do when you have an entirely on-demand labor force.
Thank you very much again, Ryan. We will be posting this recording online, and you also posted your contact details. So I'm sure some people would like to get in touch with you and discuss more.
Thank you for having me.